Okay, thank you, Mauricio. And thanks for organizing this tribute to David. It's a great opportunity to remember him, and it's very appropriate. So I know David for a long time, since late 1970s, and I've spent a lot of time with him, and so that's. I'm going to talk a little bit about the other side of his work, his theoretical work. So, David has made lots of contributions to computer science, theoretical computer science in particular. So I would like to speak about some of them. He's, as I said, a pioneer in the field. He's made major contributions to the complexity theory of NP-completeness, to approximation algorithms on the theoretical side. I mean, we've heard a lot also about his contributions on the experimental side. He's really, like Kathy said, the godfather of serious experimental analysis of algorithms. And so I'm not going to talk about that. I mean, we heard, and we'll hear some more in the next talk. And his other contribution was as a leader in the community. I mean, in DIMACS, both having started challenges here and all of these contributions, but in the broader theoretical computer science community and theoretical computer science community in particular. So I'll say a few words about that. Now, mostly I'm going to talk about some of his theoretical contributions and concentrate on a few of his papers. I'm sure all of you know them, or most of you know them well, but I think it's a good opportunity to remember them. So in NP-completeness, I mean, he's known very well for his work on NP-completeness. He has done many of the early NP-completeness results. So one of his early papers, I think that's the paper that's cited with the most citations, after the book, of course. It's an early paper he wrote with Gareth Johnson, Mike Garrett, and Larry Stockmeyer. Soon after NP-completeness came about, it was introduced in 1971 by Steve Cook. And then Dick Karp wrote his list of 20-some basic problems. So soon after that came this paper, which looked at more basic problems beyond Karp's list, and also looking at restrictions of problems, that problems are NP-complete, even if you restrict graphs to be planar, if you restrict the degree to be at most 3, these problems are still hard. So they kind of started a trend, which then was followed by many other people. Plus, they introduced more elaborate techniques. That was some of the early, more sophisticated NP-completeness reductions, which kind of taught people the tricks of the trade, how to prove results like that, and gave easier, simpler starting problems so that you can keep going. And then kind of the floodgates opened, and then you had hundreds, thousands of NP-completeness results. And they followed up with lots of other papers. This is another paper, sort of we heard about traveling salesman problem points on the plane. That's the paper that proved that this is an NP-complete problem. It's an NP-hard problem. Steiner problem, another problem that people worked on. Scheduling problems. They did lots of a number of papers on that. And lots of other papers. I should note I looked yesterday on Google Scholars, I mean, they have, the first paper has close to 4,000 citations. Same with some of the others. And furthermore, these papers keep getting cited. So they have like maybe 200 citations every year. So people, even though there is the book, there's everything, still people go back to read it and cite it. So that's, they have, of course, David has lots of other papers on NP-completeness, many of them with Mike Curry. They work, the experts on this kind of results. But another contribution and paper I wanted to bring out is David made also conceptual contribution in terms of new notions and more refined notions and terminology. So this other early paper, again with Mike, introduced the terms of strongly NP-complete problems and versus weakly NP-complete. So this is problems that have numbers. In some cases, you need the numbers to have lots of bits for the problem to become hard, like knapsack, and that's the weakly NP-complete, versus the strongly NP-complete that are hard even when the numbers are, 1 and 2 or non-existent, like traveling salesman problem. Even if the distances are 1 or 2, that's still NP-complete, and so forth. And the notion of pseudo-polynomial algorithm, the algorithm which runs in polynomial time if the numbers are not very big. Let's say you don't allow numbers that have n bits, but maybe log n bits or constant number of bits. So these are notions which are now, not now, since a few years later became everyday use, and everybody talks about strongly NP-complete and NP-complete pseudo-polynomial. This is where they originated. And in terms of approximation schemes, polynomial time approximation scheme versus fully polynomial time approximation scheme means you can have an approximation algorithm that comes within 1 plus epsilon, as small epsilon as you like, and fully polynomial, it has to run in polynomial time also in the 1 over epsilon, versus you don't need that. So these are pretty soon became standard notions, and that's where they started. Another area, in NP-completeness, of course, everybody knows about the book. This became actually, David and Mike became kind of the central station for NP-completeness results. Everybody would communicate any results they had to them. So what they did to collect everything and publish it in a book, that became a bestseller right away, and everybody is using the book since then. To this day, that's a reference book, lots of citations. And then what David did, after 2-3 years passed, people were asking them, it's time to prepare a second edition of the book because there is so many more problems. So instead of doing a second edition, he published a column with updates on the open problems in the book and some interesting new results. And once he published the first column, then he had to keep going, published the second column and the third column. And then after a while, it was not about NP-completeness. David would take an area which knew that maybe had nothing to do with NP-completeness, study it in detail, find all the references. He was, he was the scholar par excellence. He would read everything, cross-reference everything, and then write a column about it so everybody else would learn about it. So he wrote columns about all kinds of different things, interactive proofs, then total search problems, anything that became current, he would write his column. He published 26 columns altogether over the next 20 plus years. So that's really valuable. I think the community appreciated that a lot. It was a great service. Now, the other area where he actually concentrated a lot, and starting from his thesis, his work as a graduate student, was in approximation algorithms. And especially there, I think he is basically, I consider him the central person in establishing this field, the approximation algorithms. Of course, we heard about his thesis, which he did on B-packing, and an early result in Fox 72. And over the years, he published a lot on bin packing. But we heard a little bit about that, so I'm not going to talk about it. I'll talk about another paper, which he published soon thereafter, which I think is a landmark paper for the field. That's actually single-authored on the, where he looked at some of the very basic combinatorial problems. You know, graph click, coloring, set cover problem, and looked what can you say about this in approximation. So one thing he brought up is that if you consider them as, when you consider their NP-completeness, you think of them as decision problems. They are all basically the same problem. If you can solve one, you can solve all of them. But what he brought up was that as when you consider as approximation problems, they are very different problems in terms of how close you can come to the optimum. So he brought up the issue of classifying the problems with respect to their approximability, and observed that subset sum, for example, or an abstract problem, you can get arbitrarily close to the optimum. You can get 1 plus epsilon for every epsilon factor of optimum. And then he looked at these other basic combinatorial problems, like maximum satisfiability. Given a set of clauses, satisfy as many as possible. How well can you do? Maybe weighted clauses. And particularly, let's say they have k literals in every clause. So he gave one algorithm, a simple greedy algorithm, and he measured it. I mean, he analyzed it, and so that it comes to 1 minus 1 over k. So for example, for max 3SAT, you get like a 2/3 approximation. And then he gave a more sophisticated algorithm, which now is called Johnson's algorithm, which is much better, where you lose only a fraction, exponentially small fraction of the clauses, 1/2 to the k. So for example, if it's 3SAT, you satisfy 7/8 of the clauses, and at worst, you're going to lose 1/8. And that's an interesting algorithm. I don't know how many of you have seen this paper. Basically, it's kind of greedy, except that as it goes along, you take the clauses and you reweight the clauses. It's like a weight update algorithm, where you reweight the clauses as they lose more and more of their literals that you have set to false. So as it becomes more critical to satisfy it, they gain in importance. So it was a kind of strange reweighting scheme, which I read the paper as a student, like maybe 2 years after this, year after it came, which to me it looked like a magic trick, It kind of, he pulled out of the hat, how do you get these reweightings? And then many years later, in retrospect, people had started thinking about randomized algorithms and de-randomizing them. And if you think about these fractions, if you take a clause and you put randomly pick a truth value for every variable, then if the clause has, for example, 3 literals, or you will have 3 chances to satisfy it. And in order not to satisfy it, there is 1 out of the 8 possible settings of the 3 variables is going to lose it. So if you do a random assignment, it's going to lose 1/8 of the clauses. So that's a trivial randomized algorithm to get 7/8. Then if you de-randomize it by method of weighted expectations, you can get a deterministic algorithm. And if you do that, you'll get exactly Johnson's algorithm. But the thing is that when Johnson gave this algorithm, nobody was thinking about randomized algorithms. Nobody was thinking about de-randomization. This came in the 80s. So many years later, there is kind of a way to think about it to arrive at such an algorithm. But in David's case, he kind of came at it out of the blue. He just pulled the rabbit out of the hat, as far as I could tell. So, and in fact, later on, I asked David, did you think about it? He said, no, I didn't know randomization. This was not there, which I knew it was not there. He just thought about it and came up with the algorithm. So I think that was really impressive. So then you ask the question, can you do better? And David asked the question, can you do better? The other basic problem, set cover. So there is the obvious greedy algorithm. So that's the first analysis of the greedy algorithm for set cover. And he showed that that actually is not a Costa factor. It's a log n factor of optimum. And the log n is tight. In other words, there are bad instances, even in the special case where the set cover is really a node cover. Nodes covering the adjacent edges, you still greedy is going to do log n. That was, again, very nice analysis. Actually, Latsilovas did a paper at about the same time that's proving the same result. So that's, and again, it's the question, can you do better? Then the other basic problems he looked is graph coloring and click. So he analyzed several graph coloring algorithms, and people had proposed by then a number of approximation algorithms. And he showed that all of them were actually pretty bad. The approximation ratio was pretty bad. So he raised the question, okay, can you do better? Can you do, for example, log n, like set cover? And click the same situation. Oh, before I do that, so graph coloring, as I said, was people were working on graph coloring. There were several published algorithms. In terms of approximation, the fact that the problem is hard to tell if a graph is three-colorable means that you cannot tell the difference between 3 and 4. So that means there is a 4/3 gap. So another paper of David with Mike Gary pushed that 4/3 gap to make it a factor of 2 gap. And that's an early, probably maybe the earliest, a case of doing this gap amplification. Take one case where you have a small gap that it's hard, and amplifying it to show that a bigger gap is impossible. So they proved that you cannot approximate graph coloring to factor 2. The best algorithms were n to some power, or basically factor n, pretty much. Huge, huge gap. Can you do anything better? Maximum click, same problem. All the algorithms, he analyzed some algorithms that were for the click, pretty bad, basically factor n. And again, the same paper, they showed an amplification that for click, either you can get as close as you like to 1 in polynomial time, or you cannot guarantee any constant factor. You cannot guarantee 100 times the optimal, 1,000 times the optimal. So it's an either-or situation. And again, he posed this question, can you do even root n or some factor, non-trivial factor? So these problems, which were posed in that paper, people worked on it. I worked on it, for many years. Lots of people worked on it for many years. And this remained the state of the art for the next almost 20 years. Well, I think as most of you know, it took a lot of work and basically a big breakthrough, probably the biggest breakthrough, to actually resolve these questions, which were driven actually to a large extent by these questions, which is sort of the theory of probabilistically checkable proofs came into, was invented in the early 90s, basically to answer questions like that. And the answer was that these were the optimal algorithms. So 7/8 was the optimal algorithm for 3-SAT. You couldn't do anything better. Set cover, log n is the best you can do. You cannot beat that in the worst case. And graph coloring and so forth. So that's, this was, it took a lot and it's enriched the field a lot to be able to answer these questions. Now, I read this paper as a student in 75, 76. I should mention actually one thing was that I had not met David Johnson then, although I think probably he played indirectly a matchmaker role in one of my first papers in that when I read the paper, I thought about not cover. Greedy gives you log n, but there is another easy way to get a factor of 2, which is to pick a maximal matching. Matching you cannot increase, and take the endpoints of the maximal matching. That gives you a factor of 2. So then I thought, OK, can you find the smallest maximal matching? And I guess Gavril in Israel had come to the same observation and thought about the same problem. And Johnson being the central point of all communications, NP-complete, I guess told Johnson, and he told Gavril, and Gavril got in touch with me. So we worked on the maximal matching problem and wrote a paper. And that's one of my first papers before even meeting David. I met David when I went in 78 to interview at Bell Labs. So then I met him then, and then pretty soon I joined Bell Labs. And then Bell Labs at the time it didn't have all these people. By the way, I just noticed I lost one line from the first there that included Mauricio and David Applegate and other people. But anyway, so at the time, there was the Mathematical Sciences Research Center and the Computing Science Research Center, which both were doing research in theoretical computer science, among other things. So at that time, in the math side, there was Roland Graham, head of the department. There was Michael Curry in it, David Johnson. I don't remember if Shenlin was in the department or in the math center. And the other people joined afterwards. And the computer science side, there was Alejo, Ravi Sethi, and maybe 1 or 2 more people. But of course, there were lots more people on the system side. And on the math side, there were statisticians, coding theorists, all kinds of people. But pretty soon, it grew up a lot. So the department in the math center was called, I think, mathematical foundations of computing, was initially led by Ron Graham. Then when Ron was promoted, Michael Gary took over the department. When Michael was promoted, then David Johnson took the department. And in the meantime, you had Ed Kaufman, he joined Bob Tarjan for a number of years. Peter Shor, Andrew Lisko was there in another department. Lots and lots of people. And as I said, I'm missing Mauricio, David Applegates, a few more people. And on the math side, there was another department which had theory, which was led by Alejo, then Ravi Sethi. Then later on, I took over, and which had another bunch of theoreticians. So basically, that was having theory on two sides was an excuse to have twice the people. And so we basically, you heard about the theory table. We couldn't quite fit around. So if you went around, there was this table, which normally would fit maybe 8 people sitting comfortably. We would sit like 25 people around there. So it would be kind of a zones around it. You know, each one holding their plate. The people at the table would put on the table, the rest we would hold our plates and, you know, have a very lively thing. So that would happen. Nominally, it was once a week, but we would get together pretty much like every day, every other day. So for the next, let's say 78 to 96, when we split with AT&T, I would see David pretty much every day. I mean, I would walk into his office, he would walk in my office. We would often have lunch. And, you know, at the time, Bell Labs was open offices, you know. Anybody could walk into anybody's office, go on the blackboard and start writing something and have a conversation. So, very lively place. Here is a picture, mid-80s. So I think that was Peter Shor's wedding. And you can see there, David is second from left, Ed Kaufman on the left, and the bottom, Andrew Lisko, Ron Graham, Bob Wilbur, Fan Chong on the right. So this where everybody was younger at the time. I'm not in the picture. I want to talk a little bit about another paper that now we wrote together. So we have written a few papers with David. So that one is connected with you know, local search and approximation. So David was interested in approximation, both in theory, how well you can measure how well you're doing, and to, you know, how well are, you know, like different heuristics doing, like local search being the, you know, paradigm of approaching all kinds of optimization problems. So one thing we wondered about is, okay, local search, we use it on every problem. There is a question of how good the solution it finds, good. But you know, how fast, how easy is it to find a locally optimal solution? Okay, you are not asking now for global optimality, just local optimality. So we looked at this with Christos Papadimitriou, wrote a paper that's mid-80s. This picture is not from the mid-80s, obviously. It's maybe 10 years old. We defined a class for this. We couldn't fit it into the theory of NP-completeness. And there are good reasons you cannot fit it into a NP-completeness theory, because you can actually argue that, first of all, we couldn't find locally optimal solutions in guaranteed polynomial time, so we couldn't put it in P. On the other hand, we couldn't argue it's NP-hard, and there are complexity theoretic reasons that probably they are not NP-hard. It's an easier problem. So we defined this class PLS for that, where basically the problem is take your favorite optimization problem with your favorite neighborhood structure, The only restriction is that when you are at a solution, it must take you polynomial time to look at the neighborhood and to see if there is a better neighbor. So that one iteration of local search will take polynomial time. Now, how hard is it, I give you an instance, how hard is it to find a locally optimal solution? Doesn't have to be globally optimal. One way is to just do a local search. Start at an initial solution, follow the local search, and see how long it takes. But I don't restrict you to that. You can use any algorithm you like. For example, in linear programming, local search would be the simplex is the local search algorithm, right? You start with a base, and you do a swap. Take out one element and put another element and keep going. We know simplex has bad examples. But you can use another algorithm. You can use ellipsoid, or you can use Karmarkar's algorithm, interior point, to find polynomial time. How bad is it to find locally optimal solutions? So sort of concrete examples would be graph partitioning. That's one, let's say, the first Kathy mentioned, the study of simulated annealing. That's one of the problems he looked at. Graph partitioning, you want to divide a weighted graph into two equal parts. An easy neighborhood is the swap, where you swap a node from one side with a node from the other side. They have more complicated, the Kernighan-Lin neighborhood. That was part of Brian Kernighan's PhD thesis. Is a more sophisticated algorithm, finds better solutions. And similarly, you can have max cuts. You don't have to balance the two sides. You want to maximize the cut. They don't have to be balanced. A simple neighborhood is the flip neighborhood. Take a node from one side, put on the other side, and see if it improves the cut. And TSP, of course, we had 2-opt, 3-opt, 3.5 Lin Kernighan. So all these problems are in PLS. PLS is somewhere between P and NP, but it looks like it's in the middle. And the result, well, the first paper gave the first result about the graph partitioning with the Kernighan-Lin neighborhood. And other results followed that proved the same things for other local search algorithms and other neighborhoods. Basically, all of them are PLS complete. PLS complete means the most simple with the most complicated. They are equally hard to find the local optimum. And the byproduct of these proofs is also that these local search algorithms take exponential time in the worst case, pretty much no matter which rule you use to pivot, doesn't really matter. They are all exponential time in the worst case. Which was kind of interesting in that it says in the worst case, these are hard problems. On the other hand, I mean, we know from David's experiments and others that these algorithms run fast in practice. So that's kind of question, why is that? That's reflected in some sense also in the proofs. The proofs for these results are actually quite difficult. And to construct these bad examples takes a lot of sweat, which means the examples are very pathological. You really have to work hard to construct these bad instances. Anyway, so that's good. That was, I'll say two more words about that, but that was an interesting contrast. But for the, so David and I David, of course, then got full steam into the experimental analysis. I think maybe, he wanted to understand what's going on. And, did all these wonderful papers where, as everything with David, whatever he took, he was very serious about everything. So he didn't just it was not the person that would take the next problem, prove the theorem, and move on. He had to really analyze it from all aspects and do a very thorough scientific job. And his experimental papers, I mean, I'm not experimentalist, but from my point of view, they look more like theory papers than all of the other experimental papers, in that he really has considered everything. He has done like a detailed case analysis of everything, and the standards of rigor, I think, are really something else. So David went to many places presenting his work. And I went also along to many, we have done many trips together where David would talk about his experimental analysis. I would talk about the theoretical work. So I remember many, like we went to Brazil. I don't know if you were there, Mauricio. Yeah, in the 90s, on metaheuristic, great place, great conference. We went to Holland some other time. I remember it was like a school on local search that Lens Arts organized, where we gave a series of talks. So I have a lot of memories of traveling with David, presenting some of this work. So coming back to this question of the worst case behavior exponential versus the practical. So one approach to that is try to do probabilistic analysis, see if it behaves better, or maybe even better what's called smooth analysis. So probabilistic analysis, you assume some probability distribution on your hypothesis. So in this case, for example, your numbers, for example, if the numbers are the edge weights on the graph in graph partitioning, you assume they are uniform or Gaussian or something. Or if you have points on the plane, the coordinates are maybe random points. Worst case, you can see it as an extreme case of probabilistic. Well, or the probability is on one value. It's like delta functions. The probabilities are delta functions. So the smooth analysis is kind of a hybrid between the two, where you say, ask the adversary to give you their worst parameters, but then perturb them a little bit. So you're allowed to smoothen it. So you have the probabilities. It's a probabilistic analysis, but without assuming a specific nice probability distribution like uniform or Gaussian. But you assume that it's maybe an obnoxious probability distribution, but it has polynomially bounded density. It's not a delta function. And see if the algorithm does better in that case. And it did for, Spillman and Egg introduced this smooth analysis for linear programming, following a long line of probabilistic analysis of linear programming. They introduced that to try to understand why linear programming behaves well. And they showed that simplex with particular pivoting rule, this shadow vertex pivoting rule, has polynomial smooth complexity. And sort of they viewed that as a more convincing explanation of why simplex works well, in that it's not just for a uniform distribution or for Gaussian or something. And since then, there has been a lot of work on seeing what happens with other problems. And I think it's particularly interesting with local search. What does smooth analysis, what does it say about local search? And so this is kind of an ongoing active area in the last 10 years or so, looking at different. And it did for several of these PLS complete problems for local search. You can prove that the smooth complexity is polynomial or quasi-polynomial. So, for TSP with 2-opt, 3-opt, 4-opt, and so forth, you can very easily actually prove that it's polynomial. And the work, I'm not part of this work. People have worked to kind of try to push the polynomial down. For some of these other problems, this is much harder to actually bound it. Even the very simple ones, sort of this graph partitioning with swap is actually a paper from this year, so that's a very recent one. Some of these are, the last few years. There it's, and there some of them you can't, we don't know how to prove polynomial, only quasi-polynomial. The true answer probably, if you could do the analysis, is that it's low-order polynomial. But it's much, much harder to do the analysis. But it looks like probably they all have, at least we can prove it's not exponential. Probably it's polynomial. So that's this, I think if David was around, I'm sure he would be looking into this and working on that and writing a column about this and proving some nice results on that. And there is still actually a lot to do because we don't really know the precise answers, but that may be some explanation on why local search is actually performing better. Still a lot of open questions. I should say also the approximation algorithms area, which in many ways David started in the early 70s, continues to still be a very active area. So if you take two recent stock Fox soda proceedings, you're still, there is work on approximation algorithms, breakthroughs, results coming, which in real life are not changing anything. But in terms of theoretical, they are impressive and held. For example, was it last year? The year before, they broke for the TSP, for the traveling salesman problem with triangle inequality, the metric TSP. The best algorithm was the 3-half algorithm of Christophidis since 1976. The probabilistically checkable proofs theory showed that you cannot get 1 plus epsilon. There is a gap. But the gap that we have proved is very small. But nobody had beat the 3 halves until last year, basically, that was improved by a tiny epsilon, like 10 to the minus something. So very, very tiny. So people are still thinking about the approximation area very hard, and getting over this other remaining hard problems is still a major challenge for the theory community. The last thing I want to say is that I don't think we heard about contributions of David to DIMACS. Another thing, actually, I have a lot of memories is driving down to DIMACS with David. I must have driven like 100 times here to these executive committee meetings once a month, workshops, advisory boards, all kinds of things. So that's, that was a sidetrack. But besides the contribution to DIMACS, David was, I think, the most central person in the theory community, in SIGACT theory community. He started conferences like the SODA conference we heard. He was instrumental in the FCRC, the Federated Conference. He got the idea of we should have awards, the Gödel Award, the Knuth Award, Service Award. He chaired many of these conferences. He actually got the first Service Award because, it was a no-brainer. There was nobody else that compared in contributions to the community. And so his impact on the community over the years, I think, has been without comparison. And of course, those that we know him personally, we know he had lots of other sites. He mentored, had interns every summer. So lots of people went through the ranks, through the labs, and have remember him well. And, he had he loved life, music, art, everything. So he was, and plus he was always smiling. I mean, I never saw David angry. He was always smiling, talking very calmly. And so I have great memories from David. And so I'm glad we're doing the tribute here. Okay, thank you.